Bem-vindos a todos a mais colóquio da Coordenação de Astronomia e Astrofísica do Observatório Nacional. Estos são colóquios que acontecem todas as quintas-feiras, pelo geral às 15 horas, só que hoje temos a presença de pesquisador na Austrália. Por tempo, a palestra vai acontecer agora às 11 da manhã. Então, o que estou mostrando para vocês são os colóquios da agenda de julho. A próxima palestra é de simulações de sloshing no aglomerado de Galaxias Abel 1644, que vai ser apresentada pelo professor Dr. Rubens Machado, da Universidade Tecnológica Federal de Paraná. Então, estão todos convidados para assistir na próxima quinta-feira, 15 horas. O seminário de hoje está apresentado pelo Dr. Lourenço Espina, da Monash University em Austrália. Ele vai apresentar Understanding Our Galaxy, Charting a Path Forward. Antes, vou compartilhar com vocês pouco da história acadêmica de nosso palestrante. Vamos agora cambiar o idioma para o inglês, para dar o convite a ele para falar. Então, o Dr. Lourenço Espina is a stellar spectroscopist, mainly interested in the study of the galactic chemical evolution. He's a member of the Gaia ISU survey and Gala survey. Lorenzo obtained his PhD in 2014 from the University of Florence, Italy. In 2015, he moved to the University of Sao Paulo here in Brazil, and since October 2017, he has been working at Monash University as a postdoctoral fellow. So let's invite now Lorenzo to start with his presentation, and thank you very much for being here with us today.
Obrigado, Ximena. Para mim é grande prazer ser aqui hoje, porque, bom, eu tenho, como você falou, morei no Brasil 3 anos, tive a ocasião de visitar Rio também, o Observatório Nacional, tenho muitas lembranças, boas lembranças do pessoal lá do Observatório, no geral do Brasil. Então, para mim é como matar pouco de saudade esta oportunidade de ser aqui hoje. Vou tentar de start sharing. Não sei se vocês conseguem ver a primeira slide.
Sim, pode, já está.
Ok, ótimo. Então, vou passar ao inglês, porque mesmo que tinha morado lá no Brasil, já esqueci pouco de português, então para falar assim está bom, mas para falar de ciência está pouco difícil, então não quero fazer confusão. So I'm going to speak in English now. So this is the outline of my talk. It's as you can see, it's very simple. And first, I would like to give you an introduction, trying to convince you why this field is important. So the field is the study of our own Milky Way. And since our galaxy is just one of the myriad of spiral galaxies in the universe, this is an important topic not only for those like me who study actually the galaxy, but also for those working in cosmology and those who study other galaxies, and also people working on other fields. Then I will show you some of the latest results that I consider very important. So don't be scared if you are not familiar with this topic. I know that there are people at Observatório Nacional that are working on different topics, so I will try to keep it simple and understandable to everyone. It's also impossible to be completely exhaustive in 45 minutes, so I try to condense everything, and among all the results that and observational evidences that I could show you today, I have selected only the results from the observations of my favorite tracers of the Milky Way, which are the open stellar clusters and solar twins. And as we will see later, among all the objects that one can possibly observe in our galaxy, these tracers are in certain ways complementary to each other, and also they can work in synergy. So they are really important for this field. And at the same time, while I'm showing you these results, I would like also to highlight what we don't know yet. In fact, you also know we are scientists, and our job is to produce new knowledge and move the field, a certain field forward. But in practice, this is possible when we identify the most critical open questions in our field, and then we try to answer to them. At least this is my approach. So I will also outline the open questions that I consider the most strategic ones to allow a breakthrough in this field. And then finally, I will try to chart a path forward in this field by answering these questions. So let's start with this seminar. Understanding the galaxy formation and evolution, it's well known, it's a key challenge for astrophysics over the next decade. And from answers to questions like this, how do galaxies form and evolve, we can achieve a lot of knowledge about a broad variety of topics in fundamental physics, from cosmology to nuclear physics and everything in between, including stellar formation, stellar evolution, and also a better picture of the story that led us today to talk about astronomy. So in our current cosmological model, galaxies are assembled through mergers of smaller galaxies into larger ones in a universe that is dominated by cold dark matter. And even if these models have been extremely successful in explaining the large-scale structures in the universe, as we can see from this picture here, our understanding of galaxy formation evolution is still incomplete. And in particular, we still do not understand very well how galaxies reach their present-day properties. So in order to fill this gap, there are two possible approaches. We can study thousands or millions of galaxies in the distant universe with an excellent statistics, but a very blurred view of each of the galaxy, or we can study our own galaxy in very good details. My research is mainly based on the second approach, and in particular, I'm mostly interested in the study of the galactic disk, which contains a lot of information simply because it contains the largest number of stars and also the most of the angular momentum of a galaxy. The problem, as we will see later, is that we are still not fully sure how we can extract this, the full information that is locked into this galactic component. So we're living in a very special era of the galactic astronomy, and I think I've been very lucky because since the beginning of my PhD in 2011, I have seen this field changing a lot. So I've seen things changing, like changes in the approach, in the method of analysis, and all these changes are mostly due to the start of the large galactic surveys. For example, since 2011, we had Gaia, which is providing position, parallaxes, proper motions, radial velocity, photometry for nearly 1% of the entire galactic population. Here in this figure here, we can see a representation of our own galaxy and how Gaia is mapping the galaxy. So it's impressive how many stars have been observed by this survey. And then we have other spectroscopic surveys, such as Apogee or Gaia ISO survey and Gala. I'm sorry if I have not named your favorite survey. There are many more spectroscopic surveys, but I only have 45 minutes, so I have to be quick. But the main point here is that all these collaborations, all these surveys have started a revolution in our field by producing a real tsunami of data. So how are we using this data? If I want to resume my job in a couple of lines, then I will say that I study the property of stars to gain a physical understanding of the sequence of events which led to our present Milky Way. So I study the property of stars, such as the position of stars, their kinematics, the ages and chemical abundances, to understand how the Milky Way formed and evolved. For example, our final aim is to answer to broad questions like this one. How was the Milky Way disk assembled? How does it evolve with time? So first of all, we must understand that galaxies are like factories that convert the gas into stars. And in the process, they constantly evolve. Elements are fused into heavier ones by stars, and then they are dispersed into space, where they become the building block of a next generation of stars. So younger stars have heavy elements in a greater abundance than older stars. So it's possible to link this chemical buildup to the history of galaxies by studying the chemical composition of the stars in our own galaxy. So for this reason, the history and the evolution of the Milky Way is often examined against this plot here, which is very famous for those who are in the field. And this plot shows the alpha elements over iron as a function of the iron metallicity. This is a very important plot because the alpha elements, for example, silicon or titanium and iron, are produced by very different nucleosynthetic channels and on different time scales. In particular, in this plot, which was made by my PhD student, Giada Casali, the stars are also color-coded as a function of the age of their age. So it's immediately clear, for example, that the galactic disk is composed by two stellar populations that are clearly distincted also in chemical composition and in age. We have an old alpha-rich population, which is this banana here, and a younger alpha-poor population. So now let's consider the alpha-low population. We can see that the metal-poor tail is older than the metal-rich tail. And this is very simple. This is the consequence of the chemical enrichment. So new iron has been produced with time, so younger stars in the galaxy have formed in an environment that was metal-richer. So they resulted to be metal-richer than the older stars. And it's also possible to study how these stars are distributed in space along the galactic disk. For example, in this plot here, I'm showing basically the same plot of before, but in different bins depending on the location of within the galactic disk. So in each row indicates the distance from the galactic plane. This row here indicates the stars that are in the mid-plane, while these rows here indicates the stars that are far from the mid-plane, while each columns indicate the distance from the galactic center. So here we are close to the galactic center, and here we are in the outer disk. If we still look at the metal of the alpha-poor population, we can clearly see that the metal-richer stars are preferentially located as small galactocentric radii closer to the galactic center, while the metal-poor stars are located at the outskirts of the disk. And this happens because closer to the galactic center, there is a much higher density of stars. Thus, the chemical enrichment proceeded at a higher speed than in the outer disk. So in this introduction, I don't want to be completely exhaustive about this, and I don't want to enter into many details, but I just want to give you two very simple examples of among many, many others on how we can use the chemical abundances to infer something about the history of the Milky Way. So we want to use this data to achieve a quantitative information about our galaxy. And to do so, we can compare this data to predictions, for example, to prediction of galactic models, which are also central in the study of our own galaxy. And these models generally depends on a scenario, which is a sequence of events, and other quantities that are related to the physics of the galaxy and the stars. Of course, observation can provide constraints on the physics, but the problem, in my opinion, is that nowadays there is still a lot of friction on the possible scenarios. So we are still uncertain on the possible scenario that led to our present day galaxy. And this confusion, still in my opinion, is mainly due to the fact that stars migrate within the galaxy. We know that stars, most of the stars have traveled a long way from the orbits in which they are born, and now it's difficult to figure out where they came from. So for example, if I observe a star that is close to the sun, no one tells me that the star actually formed in the solar vicinity or formed in another region of the galaxy. And of course, this radial migration has shaped the distribution of elements that we observe today along the galactic disk. For example, in this plot here, we see the result of an n-body simulation of our galactic disk, and the results shows that a fraction of stars that are now in the solar vicinity, so now that are now located in the red band, for example, they actually formed at very different locations. Yes, some of them formed in situ, but many of them formed in the inner part of the galaxy and in the outer part of the galaxy. And as I said before, this radial migration has shaped the distribution of elements that we observe today. And this we can see this in this other plot that is the result of another n-body simulation, where we can see that the metal-rich stars in the solar neighborhood, so with metal-rich, I mean here the stars that have an iron abundance greater than -0.1, actually most of them formed in the inner part of the galaxy. So it's this radial migration produces a bit of confusion, and the radial migration can be of two types. We can have a blurring when stars migrate simply because it's on a very eccentric orbit. So the stars, when it orbits around the center of the galaxy, spans different galactocentric radii, and in this migration the stars conserves the angular momentum, while we can have a churning, and if we have churning means that the star is progressively gaining or losing angular momentum from interaction with the gravitational potentials, for example the spirals or the bar of the galaxy, or giant molecular clouds. So this interaction, gravitational interactions, can make the stars change in the angular momentum and migrating through the galaxy. So the problem, in fact, is that we are currently lacking of a reliable method that could allow us to disentangle the distribution of stars that we can observe today along the galactic disk from stellar migration. And we are not even completely sure about the relative importance of these two processes. And as we will see in the next slides, this is one of the key problems that we need to overcome during this decade. As I have mentioned before, I'm studying the history of our galaxy using an observational approach, and in particular, I love to observe open clusters and solar twins. But let's start with open clusters. So open clusters, in fact, are unique tools to answer to the questions that I have outlined before. For example, how the Milky Way is structured and how does it evolve with time. Open clusters are a homogeneous group of stars that form together at the same time and from the same material. And this means that they are stellar populations that are very, very simple to model, as their members approximately share the same distance from us and from the galactic center, and also the same age, the kinematics and chemical composition, and so on. So as a simple stellar populations, their ages, distances, and chemical composition can be determined with an extremely high precision compared to the field stars. So we know that open clusters are many in our galaxy. So one of the latest census of open clusters counted around 1,500 of open clusters in our galaxy, but for sure there are many, many more. They are spread throughout the entire galaxies, and they are mostly young, but their ages cover the entire history of the low alpha population that we have seen before. And they are mostly young because they can dissolve. So clusters are not expected to survive for a long time, but some of them do. So thanks to all these properties, for example, open clusters are extensively used to trace the galactic metallistic gradient. So the galactic metallistic gradient describes how the average metallicity of stars changes as a function of the distance from the galactic center. So this is the distance from the galactic center, and here we have the metallicity, and we can see that there is a gradient here. So therefore, this gradient provides a fundamental insight on how the chemical enrichment has proceeded at different locations in the galactic disk. And it can also give us hints on many other topics and factors that can have affected and led the evolution of the Milky Way. So, for example, the stellar yields, or stellar formation rates, or dynamical properties of stars, or even the existence or not of dynamical barriers in the disk. So it has become common in the literature to model this gradient with a broken line and a knee located around 12 or 13 kiloparsec from the galactic center, as you can see here. And this led to the conclusion that the outer disk is uniformly metal poor, while the inner disk has undergone a chemical enrichment that was more vigorous as we get closer to the galactic center. As we can see here, in fact, the closer to the galactic centers, the stars are richer. So the chemical enrichment has been quicker and more efficient. So this model in particular assumes that there is a sort of chemical continuity between the inner regions of the disk and the outer regions of the disk, in contrast to other studies like this one, for example, that suggest that the distribution of clusters can be reproduced equally well by a step-like function like this. So such an abrupt step would indicate that the outer disk has evolved and maybe even formed in a completely different manner than the inner disk. So the consequence of this model will be that the galactic disk, which is commonly considered as a unique component of the galaxy, should instead be considered as the union of two separate stellar populations. I think that this is a really interesting debate, also considering what we are observing in our other spiral galaxies. In fact, in other spiral galaxies, we are observing gradients that are both types. So we have both of these types here. However, to be fair, this is one of the latest observational evidences on this topic that has been provided by a sample of around 70 clusters observed by Apogee, survey Apogee, and it seems to disprove the existence of a chemical discontinuity located at 9 kiloparsec. I cannot really see any discontinuity from this data here. However, this is a really interesting evidence, in my opinion. This is a really interesting evidence, but is probably is not the most interesting result published in this paper. In fact, open clusters, as I said before, are objects that can be easily dated, and they can also be used to study how the galactic gradient evolved with time. So now let's try, before looking at the results, at the data, let's try to do a mental exercise. So we have said before that the galaxy is constantly producing new metals, and because of this chemical buildup, younger stars are metal richer than older stars. And I've also said that this chemical evolution in the inner region has proceeded at a higher speed than in the outer part of the disk. So one would expect, I think it's a wrong slide. Okay, one would expect that the young gradient, so the gradient that is traced by the younger clusters, will be steeper than the older gradient, so the gradient traced by old clusters. And if this is not enough, then we can also make another consideration. So I've also said that the stars can migrate across the galaxy, and in principle, open clusters should do the same. So this is producing a radial distribution of metals across the galactic disk with time. And this would also lead to a flattening of the older gradient relative to the young one. So this will confirm also this. Instead, as often happens in science, reality is much more complex than our predictions. Probably this is also why we love science. In fact, for example, donor and collaborators, by the way, Katia Cunha is also one of the authors of this paper. They have divided the open clusters in different age bins, and they have observed that young clusters, that the gradient traced by young clusters is actually flatter than the gradient traced by old clusters. So basically the opposite of our expectation. And this is also evidently adopts with what we would expect from galactic models. If this is not enough, we can also add that for field stars, the things go in an opposite way, more in agreement to our expectations. So in fact, as you can see here, the black line and the gray area are the data, while the dots are just models. So let's focus on the data, so the gray area. You can see that for young stars, the gradient is steeper, while for old stars, the gradient is flatter. So exactly the opposite of what we observe with open clusters. So evidently there is something that needs to be explained about open clusters, and that this difference could be between open clusters and field stars could be explained by suggesting that the open clusters and field stars migrate within the galaxy in different ways. And this makes perfectly sense to me, because the phenomena that makes stars migrate So the interaction with strong gravitational potentials, such as the giant molecular clouds or spirals or the central bar, are the same that can disrupt clusters. So a star that interacts too often with one of these potentials will simply migrate, but a cluster that interacts too often with this potential will dissolve and terminate its life. So this is still an hypothesis, and it's still an open question, but I think it's a very important open question, as we will see after. And in addition, I think that is still not very well explained why the gradient traced by young clusters is nearly flat. And in fact, there is something strange that is going on with the young clusters, I will say, as it evident also from other studies. In particular, this result reminds me of some studies that we obtained in the past. This was the slide that I had to show you before. So, for example, in my career, I have studied a lot young clusters. In particular, clusters that are younger than 100 million years. And why? Because young clusters are very important tracers. They are the latest products of the Milky Way, so they are essential to put the strong constraints of the galactic models. And also, young clusters are young, so they didn't have time to migrate along the galactic disk, so their chemical composition is truly representative of the chemical composition of the interstellar medium where they are observed today. So in 2014, we published a paper where we compared the chemical composition of the young clusters in the solar vicinity. With solar vicinity, I mean all the clusters that are within a 500th of parsec from the sun. So we compared the chemical composition of these young clusters in the solar vicinity to the chemical composition of all clusters that are contained in this volume. And this is the metallicity distribution of all the clusters in this volume. As we can see, they cover a large range of values. But if we consider only the young clusters, we can see that they are mostly restricted to the lower part of this distribution. And the strangest thing is that if we consider only the stellar Fermi regions, so the youngest associations of the young clusters, so objects that are younger than 5 million years, we can see that there are no metal-rich star Fermi regions in the solar neighborhood. And this is exactly the opposite that one would expect. One would expect to observe that the youngest stars are also the richest, but this is not the case in the solar vicinity. So there is something strange. And also, a few years later, we observed some other clusters, not in the solar vicinity, but also in the inner part of the galaxy. And while, for example, in this plot, while the black dots are all the clusters, and we can see that they trace the gradient, a steep gradient, the red dots are stellar Fermi regions, so very young clusters. And we can see, for example, this is just 1 point, okay, but it seems that it's much metal poorer than it should be compared to the older clusters located at a similar distance from the galactic center. And last but not the least, Orion. Orion is a very interesting region. I think that Katia Cunha knows it very well because she basically started the topic that I'm going to talk about now. So Orion is a complex of subclusters of different ages. We know that these subclusters form from the same giant molecular cloud, and that started to collapse in the northern outskirts. And then the explosions of the most massive stars have sequentially triggered a different stellar formation episode towards the south. And we can still see evidences of gas that has been compressed by this explosion, for example, here. We also think that these explosions have progressively enriched the gas of new metals. So one would expect to observe the youngest regions, for example, the Orion Nebula Cloud, to be richer in metals than the oldest regions. Instead, we observe the opposite. We observe, for example, that the youngest region is also the poorest. So there is something strange. So if you are lost, I will do a small recap of what we have seen so far about open clusters. We have seen that open clusters are many. They are spread throughout the entire galactic disk, and they span a large range in ages. We have seen that they can be used to trace the galactic radial metallistic gradient and its evolution with time, but with results that seems to be in contrast with what we would expect from the galactic models and from observation of field stars. And finally, I have outlined some open questions that I think are really important. So, for example, do open clusters and field stars migrate in similar ways? Why is the young gradient flat? So the gradient traced by young open clusters is flat. And why the youngest clusters are poorer of metals than the older ones? I don't think we could say we have understood what's going on in our galaxy without having answered to these questions. However, as I said before, I am also expert in the observation and analysis of other traces in the galaxy, which are the solar twins. And in fact, solar twins may provide some clues on these questions. So first of all, I have to explain which is a solar twin. So a solar twin is a star with atmospheric parameters that are very similar to those of the sun. And they are important because through a line-by-line differential analysis relative to the sun, we can get rid of most of the systematic uncertainties that affect spectroscopic analysis. And we can obtain very high precision in stellar parameters, but most importantly, in the stellar ages and abundances. So in conclusion, solar twins among all other stars, as we can see from this picture here made by one of my collaborators from the United States, solar twins are spectroscopically friendly stars. And through the analysis and the study of solar twins, we can study the chemical history of the Milky Way with the highest precision possible. Of course, this does not come for free. And in fact, to achieve such a high precisions, we need to acquire the spectral solar twins at very high resolution and very high signal to noise, meaning that we can perform this kind of studies only for the solar twins that are closer to us. So typically closer than 100 or 200 parsec from the sun. Nevertheless, in the recent past, we have obtained many interesting results. For example, with the precise ages and chemical abundances, you can trace the chemical enrichment of the galactic disk. In this plot, I'm showing the ratio of some elements of Orion. How I'm showing how these ratios are changing during the history of the Milky Way disk. And we can see that the stars trace different distributions accordingly to the time scale of the nucleosynthetic channels for each of these elements. And since different elements are produced through different nucleosynthetic channels and on different time scales, we can use the abundance ratios of some specific elements as chemical clock. For example, we can use the ratio between the S-process elements like yttrium and an alpha element like magnesium as a chemical clock. In fact, the ratio shows a very neat and tight correlation with age. So we can use the ratio abundance for the star to to try to infer or to determine the age of the star. And the same happens for yttrium of aluminum, for example. As I said before, however, to reach such a high precision, we need to observe only the stars that are closer to us. And this means that these studies are only valid for the stars that are located in the solar neighborhood. And it is not expected that these relations will look the same in different parts of the galaxy. For example, my student Jada in a recent work has calibrated the yttrium over magnesium chemical clock on a sample of 500 solar twins in the solar vicinity, and has applied this relation, the chemical clock, to try to re-estimate the age of open clusters located at different galactocentric distances. So what we found is that while there is, for example, here we are showing the difference between the age estimated by the chemical clock and the age from the literature of these clusters as a function of the metallicity of the clusters. And while there is a good agreement for the clusters that are located in the solar neighborhood and in the outer disk, it seems that the chemical clock that for the clusters in the innermost regions of our galaxy, the chemical clock has systematically overestimated the age of these clusters. And this implies that the chemical clock that we have calibrated from stars observed in the solar vicinity cannot be used anymore for stars that are formed in other regions of the disk. In fact, if we look outside of the solar neighborhood, we have to deal with the complexity of the galactic chemical evolution. And this complexity, for example, includes a radial variation of the stellar formation rate and different speeds of galactic chemical evolution. So, resuming, we know that all galactic, we have many galactic surveys that are collecting a huge amount of data, but from this simple result, it's immediately evident that in order to fully extract and comprehend the information that is locked into this data, it's essential to understand how stars migrate within the galaxy. It's essential to understand if the star that I'm observing actually formed here close to the sun or in another region of the galaxy. And this is not the only challenge. It's one of the main challenges, but it's not the only challenge of the current decade. For example, last year, we have analyzed a spectrum of a young and active solar twin taken, and whose spectra were taken at different phases of the activity cycle. Here it's the activity index as a function of time, and we found that some spectral lines, those that are formed closer to the stellar surface, where the magnetic fields are stronger, change as a function of the activity level. And because of this effect, the star appears to be metal poorer than it actually is when the activity is higher. So 1 year later, we have repeated the same experiment, but on a much larger sample of solar twins, observed many times along the activity cycle. And we found that when the star is quiet, so this is another activity index, when the star is quiet and the stellar activity is low, the spectrum does not change significantly. But when the star is active enough, then the star appears to be metal poorer than it actually is. So now you should consider that young stars are active stars. So this from our results, we can conclude that the young stars appear to be metal poorer than what they actually are. And this phenomenon, in my opinion, can easily explain the fact that the young clusters in the solar vicinity appear to be metal poorer than what we expect, and probably that what probably are in reality. And it's also possible that this effect have played a role in make the younger gradient flat. So now we are moving to the last part of my talk. I only have a few minutes, so I will go very quick. So as a stellar spectroscopist, I'm interested in the study of a chemical evolution of a galaxy, and I can identify two key issues that need to be addressed as soon as possible during the current decade to fully exploit the richness of data that are coming from this galactic surveys. So first, we need to face the fact that stars are complex objects and cannot be entirely described by only few parameters like temperature, radius, and metallicity, but there are many other factors, such as, for example, the stellar activity or the presence of stellar spots that, if ignored, can lead to misleading results. And the second issue is that the stars migrate, and we need to understand how they migrate in the galaxy. So there are different works that have been proposed to try to disentangle the effect of stellar migration from the disk. And these works are based on the assumption that the chemical makeup of a star provides the fossil information on the environment where it had birth. And therefore, with precise chemical abundance measurement, we may be able to reconstruct the origin of this to determine the origin of the star, the origin location of the stars. So the idea is very simple. You can assume a model that describes how the interstellar medium chemically evolved in space and time, and knowing the age of a sample of stars and their metallicity, you can simply tag the star to the galactocentric radius at which it formed. For example, these are young stars, and you can do this operation for these young stars, and these are slightly older stars, and you can do the same operation for these stars. The big problem is that this method strongly depends on the model that is employed. Therefore, you cannot use the results to put constraints on the model itself, because it will be a circular reasoning. However, it's possible that the solution could come from open clusters. Now I have to be very fast because I'm late, but it's possible that the surviving clusters are those that have conserved the most of the angular momentum. And this is simply because the clusters, if they are subjects of the interaction with this gravitational potential, they would dissipate quickly. So the surviving clusters, it's possible that the surviving clusters are those that have not interacted much with the spirals and the bar. So if this is true, then we could simply use the open clusters to tag stars back to their origin. And there are many indications that this could be true. I have to skip, so in practice, one could study, for example, the spatial location of clusters and compare them to the location that are predicted by models. Or one could also study how clusters move in the galaxy compared to field stars, or even the chemical dispersion of clusters along the galaxy, and compare the chemical dispersion to field stars to check if actually they are a similar population, if the open clusters have migrated similarly to field stars or not. In particular, for example, I would like to highlight these things, and then I will finish. We can see from this picture here, for example, that the clusters in our galaxy are far from the galactic center, while there are many models of observation of sorry, there are many models of galaxy formations that predict that clusters form preferentially in the inner part. So there is a difference between the models and the observations, and one would have to answer to this question as well. And this hopefully will lead us to some hints on how clusters migrate compared to field stars. So this is my take-home messages. I just want to highlight this part. We have to understand how, if it's true that the surviving clusters have conserved most of their angular momentum or not. So if the surviving clusters are those that have are not migrated much in the galaxy. If the answer to this question is yes, then this will be a complete revolution in galactic archaeology, because I could then I could use open clusters to trace back the stars to their birth location. If the answer to this question is no, then this will provide anyways very important details and clues on different topics related to the study of the galaxy. So I will stop here. I'm late of a few minutes, and I will take your questions.
Okay, thank you, Lorenzo. Thank you very much. It was a great talk. It was easy to follow the outline, so thank you. But I have some questions. Okay. I'm going to give some time to the people in YouTube to make some questions, and I have some. Could you give, because you talk about the inner and the outer disk, could you give any overview of the state of art understanding of the thin and the thick disk?
Yes. In particular, what do you want to know? It's I can, if I can go back to,
if you can find any substructure also in the thin and the thick disk, as you find in the inner and in the outer disk.
So the inner, sorry.
Yeah.
So are you asking about the thick and the thin disk, or the inner or the outer disk?
My question is about the thin and the thick disk, okay, but relative to find any substructures there, as you find in the inner and in the outer disk.
Yeah, so there are some structures, there are some things that needs to be explained, but in particular, as we can see here, actually we can see better here, the thin disk, so the low alpha population is located at all the galactocentric radii, and also it's located in what I call the outer disk. For me, the outer disk is something that starts at 9 or 10 kiloparsec. So, but you can see here that the thick disk is not present anymore at this in the outer part of the disk. So it's not present anymore, and so this is the main feature that I will say differentiate these two populations. There are other features, for example, especially in the younger population of the thin disk, that has been observed, and we see from Gaia that there are some features also related to the kinematic of stars, and there are some waves that we observe that are probably due to the fact that our galaxy has engulfed other galaxies or other massive objects that have produced a wave of stars in the disk. So I don't know if I have answered to this question. It's a very broad question, so it's a
I know, sorry, but yes, This is because I'm not from this area, so
Okay,
that's
no,
why
no, no.
but yes,
there are many interesting things that are constantly discovered, especially during the last months when we have started to look at the Gaia data. So it's really interesting to be able to work on this field nowadays.
Okay, and another question, because I'm not from this area, I'm not relative to this area. Is there any relation between the mass of the stars and the metallicity gradient of the disk?
No. So in principle, a mass, the metallicity of the star depends on the environment where the star has formed, regardless its mass. So it depends, yeah. So a cloud, when the cloud collapses and starts to form stars, the cloud can form a very low mass stars, but also can form a high mass stars. But all these stars formed from the same cloud should have exactly the same composition because they form from the same material.
Okay. And my last question is, you talk about an enrichment of the disk. So we have a model that explain that mechanism. Can just supernova explain the metallicity, the enrichment metallicity?
Not only supernova, there are different, I call them channels of nucleosynthesis, but with channels, so there are many different processes that can produce new elements and release these elements in the medium, in the galaxy. So HEB stars, for example, is another process that is not a supernova, but is just a star that is not as massive as stars that will end up in a supernova, but is a less massive star. And at a certain phase, it will start to make pulsation and release some of the products of the new elements that the stars have formed into the space. So producing new elements that then become available for a next generation of stars. And of course, there are many models that try to link this production to the evolution of the galaxy, and in particular to the data, so to this data, trying to explain, trying to link the models to the data. And but of course, these models depend on different things, not only the physical properties of the galaxy and stars and different yields, but also on different scenarios. So there are models that assume a different sequence of events and that could predict different things. Yeah.
Okay, that's right. So now we have a question from another professor of the Observatorio Nacional, Simone. She's going to ask you a question. Hi, Simone.
Hi, hello. Hello. Thank you, Lorenzo, for this nice talk. It's well, you have shown some the impact of migration in the gradient, but for example, for young stars like B stars that haven't had time to migrate yet, so they represent the composition of the place where they have been formed. But the distribution of chemical composition, of oxygen composition of B stars in the outer disk, they show a large spread. So maybe this couldn't be an effect of migration, of course. So how to explain this large spread? Maybe I think maybe when you look at the radial gradient, we consider radial, all the projections in a given radial direction. L equal 0, but we don't consider, generally we don't consider the azimuth. Well, it had been some studies about azimuthal gradient, but it's quite inconclusive up to now. But I think there are differences between regions, stars that has been formed on the arms, or in some places between the arms. So I think this effect is not being considered in the case of B stars. What do you think about this?
Yeah, I completely agree. You are completely right, and probably you know the topic much more than me, but about oxygen and this thing and these elements. But yes, and in my studies in particular, I focus my studies on stars that are close to us. So I compared, for example, the stars in Orion and or stars in the Pleiades or Hyades, and we find that there are differences in the chemical composition between these associations that are not only at the same galactocentric distance, but they are really especially close together, and we still find the differences. So it's I think it's really interesting and intriguing, and I think there are still many open questions. In my opinion, there are many question marks, not only related to the physical distribution of the elements in the galaxy. So, for example, as you said, the azimuthal, there could be an azimuthal gradient or things like that. But I think that another possibility could be also related to the physics of the stars that are not very well modeled. I'm talking about, in particular, solar twins or solar type stars. So I know that massive stars are, or OB stars are very different objects from solar twins. So, but for at least for solar type stars, what we are finding is that really the spot, the filling factor of the stellar spots, and also the strength of the magnetic fields is something that can change a lot some specific lines, and have led us to misleading conclusions. So this is something that I hope in the future I would like to investigate more, because I think it's a key factor that we need to take into account in order to decide or not if the stars in a determined region are actually chemically homogeneous or not. So I think it's a very complex topic, this one. Yeah, but
yeah, I think most of discussions about gradients are reduced to the slope, but this topic's much richer than this. You know, there are many other questions. It's not a question about the slope. It's minus 0.4 or minus 0.7. It's not only that.
Yeah, and I can also add something. I didn't have the time to talk about it, but the disk is roped. So since the disk is roped, when we, I don't know, this is the camera. When we talk about distances, actually we are underestimating the distance of the most distant clusters, because the disk goes down. So it's a really, as you said, I completely agree with you. It's a very complex topic. It's hard to put all the information in 45 minutes, and also I've been very late, so so I try to do my best. But yes,
it was a great talk. But always we find that if you just split in all the samples of the studies of radial gradients, if you split the distribution of data in two, you usually find the distribution of the inner objects is more homogeneous, and in the outer disk you find some more dispersion. So this seems to be something that result that you find in different studies. But again, in the outer disk, it seems that the gradient may be flat or not really, but because of this high dispersion. But in the inner disk, you have some more homogeneous abundances. But the slope, sometimes you cannot be sure about the slope in the inner disk, in the very inner disk of the disk, region of the disk. So it seems it's not clear what's the observational constraint that we really need for the models. What do you think it's more should have more impact in this topic? To study the inner disk or to study the outer disk?
This is a very difficult question. I will say that probably, so if I want to be diplomatic, I will say both. But probably the inner disk contains more information about the evolution of the galaxy and how the evolution proceeded. And in fact, as I showed before, and also as you said, the clusters in the outer disk, they trace a nearly flat gradient. So there is not much information, I would say, studying these galaxies, or at least focusing only on these galaxies will not give us a lot of information probably. But in the complexity, and in particular, considering also the clusters in the inner disk, I think that will be interesting. For example, I think that this, even if I don't believe to this step function here, but I think it's a really intriguing consideration. So, because it tells you that really, if you study the chemical distribution of open clusters, both in the outer disk and the inner disk, you can clearly see, you can clearly gain insight on how the galaxy formation proceeded. For example, these authors that are also Brazilian, they proposed that this step function could be the result of a dynamical barrier that didn't allow to the stars and the gas in the inner part to move to the outer part, and also the opposite. So I think that the complexity, so the entire population of the disk will allow us to proceed on this topic. And also there are not only clusters, there are also cepheids or other tracers, or clouds. Also, we can also measure the chemical abundances in clouds or in massive stars, oxygen in massive stars, for example, and so on. So there are many tracers also in the inner part of the disk that are interesting to look at.
Yeah, but on the other hand, most of the models, they predict different behaviors in the radial gradient in the outer part and not in the inner part. So maybe if you get a robust result for the outer part, of the gradient, it's more likely that you can choose what's the best chemical evolution model.
Okay, yes, I see what you mean. Yes, yes. Probably that's true.
Yeah. But also in the inner disk, very inner disk, we don't have the data. It's difficult to work there. So yeah.
Yeah.
Okay, thank you.
Thank you.
Okay, so we are going to finish now because it's so late there in Melbourne, and we thank you, Lorenzo, very much for being awake until so late, and we appreciate your presence here today with us. Thank you.
Thank you to you.
So,
Thank you.
Então, agora vou falar um pouquinho em português para lembrar vocês que a próxima palestra é na próxima quinta-feira, 15 horas, e é simulações de sloshing num aglomerado de galáxias Abel 1644 do professor Dr. Rubens Machado, da Universidade Tecnológica Federal de Paraná. Então, dessa forma, nos despedimos. Até a próxima. Muito obrigada.
Muito obrigada, Ximena.
Tchau, tchau. Obrigada.
Obrigado, Lorenzo.
Tchau, tchau.
Obrigado,
Bye.
Ximena.
Obrigado para vocês.
Obrigada.